Here we prove the following theorem. Beta v1 to vm is a basis for v if and only if each vector in a subspace V can be uniquely expressed as a linear combination of the basis vectors. So suppose we have a basis V1 to Vm, so that V can be expressed as C1 V1 plus C2 V2 plus Cm Vm. Now suppose it is not uniquely expressed as linear combination. So there's another combination, D1 V1 plus D2 V2 plus Dm Vm equal to V. And suppose that V1 and Vm are independent, as they are as basis vectors. Then from the equality star, if we put all the terms with a D on the left hand side of the equation, then we get C1 minus D1 V1 plus C2 minus D2 V2 plus Cm minus Dm Vm equals the zero vector. Now here we have a linear relation between V1, V2 and Vm. But since these Vn, these vectors Vi are all independent, we must have that only the trivial linear relation exists between these vectors, so that C1 minus D1 equals C2 minus D2, etc., till Cm minus Dm equals 0, which means actually that C1 equals D1, C2 equals D2, etc. So now the other way around. So suppose each vector V and V in the subspace V can be uniquely expressed as linear combination of the basis vectors, so that we have V is C1 times V1, etc., plus Cm times Vm, and this expression is unique. Then also we have a unique expression for the vector V is 0. So since we have that the 0 vector is 0 times V1 plus 0 times V2, etc., plus 0 times Vm, and the fact that this is the unique linear relation delivering the 0 vector, there's a unique linear relation between vectors V1 and Vm, which gives the 0 vector. We must have the following. So if we express the 0 vector as C1 V1, etc., plus Cm Vm, then these coefficients, these scalars C1 till Cm, should all be 0. So due to this implication, we have that V1 and Vm are linear independent by definition. Also note that since each vector in V can be uniquely expressed as linear combination using these vectors V1 till Vm, we know that V is actually the span of the vectors V1 till Vm. So we have now two characteristics of a basis. First of all, V equals the span of the vectors V1 till Vm, and also V1 till Vm are linear independent. So this means that actually B equals V1 till Vm is a basis for V, which we needed to show.